Good morning everyone. My name is Melvin Matthew and today I am going to present my seminar on expert system architecture. Expert systems are one of the earliest and the most successful applications of artificial intelligence. They are designed to imitate the knowledge and decision-making ability of a human expert in a particular domain. These systems are widely used in areas such as healthcare, banking, manufacturing, education, and technical support because they can provide fast, accurate, and consistent decisions. In this presentation, I will explain what an expert system is, how it is evolved, its architecture, its major components, and how all these components work together to solve real-world problems. So let's begin by understanding where expert systems fit within artificial intelligence. Before understanding expert systems, let's first understand artificial intelligence. Artificial intelligence is the science of creating machines that can simulate human intelligence. These machines can perform tasks such as reasoning, learning, problem solving, and decision making. The main goal of AI is not only to understand how human intelligence works, but also to build intelligent systems that can perform complex tasks efficiently. As shown in the diagram, artificial intelligence has several important branches including natural language processing, robotics, machine learning, and expert systems. Today our focus is on the expert systems branch. Unlike machine learning, which learns from data, expert systems rely on predefined knowledge and logical rules provided by human experts to make decisions. This makes expert systems especially useful when consistent and explainable decisions are required. So what exactly is an expert system? An expert system is a software application that mimics the reasoning and decision-making ability of a human specialist to solve complex problems within a specific domain. Instead of thinking like a general human, it behaves like an expert. For example, a doctor, an engineer, or a financial advisor. On the right side, we can compare a human expert with an expert system. A human expert has limited availability, may become tired, and performance can vary depending on experience and fatigue. In contrast, an expert system is available 24 hours a day, provides competitive and consistent decisions, and produces results almost instantly. It is also highly reliable because it follows logical rules instead of emotions or personal judgment. These advantages make expert systems valuable for organizations that require accurate and repeatable decision making. Expert systems have evolved significantly over the years. The journey began during the 1960s with Dentrel, one of the world's first expert systems. Dentrel was developed to help scientists analyze chemical compounds and generate hypotheses automatically. In the 1970s, mycin was introduced. Mycin was designed for the medical field, where it diagnosed severe bacterial infections and recommended suitable antibiotics. In 1978, another important expert system called XCON was developed. XCON became a commercial success because it automatically configured complex computer systems for digital document corporation. Today, expert systems continue to evolve as part of a modern AI. They are now integrated with technologies such as IBM Watson, cloud computing, and intelligent healthcare systems to provide faster and more accurate decision support. Now let us look at the core characteristics of an expert system. The first characteristic is that it is knowledge based. This means the system depends on a large collection of domain specific facts and expert knowledge stored in its knowledge base. The second characteristic is reasoning. Instead of simply storing information, the system applies logical rules to analyze facts and reach meaningful conclusions. The third characteristic is decision making. After completing the reasoning processing, the expert system recommends the most appropriate solution or action. Another important characteristic is reliability. Since expert systems follow predefined logical rules, they are not affected by stress, emotions, or immune fatigue. They also provide high accuracy, reducing the possibility of human error. Finally, expert systems ensure consistency. This means the same output will always produce the same output, making them dependable for critical applications such as healthcare and finance. These characteristics explain why expert systems are trusted in many professional environments. This slide shows the overall architecture of an expert system, which illustrates how all the components work together to solve a problem. Let's start from the top. Here the user is the person who interacts with the system. This could be a doctor, engineer, bank employee, or any other user seeking expert advice. The user communicates through the user interface, which acts as a bridge between the user and the expert system. It accepts the user's input and it displays the final recommendation. Next is the inference engine, which is often called the brain of the expert system. It analyzes the user's input, applies logical reasoning, and determines which role should be used. To make decisions, the inference engine consults the knowledge base, which stores facts, rules, and expert knowledge collected from specialists. It also uses the working memory, which temporarily stores the current information and intermediate results while solving the problem. At the bottom, we have the domain expert who provides specialized knowledge and the knowledge engineer who converts their knowledge into rules and stores it in the knowledge base. All these components work together to provide intelligent and consistent decisions, making the expert system behave like a human expert. Now, let's take a closer look at the first two components of the architecture. The user is the person who seeks advice or a solution from the expert system. The user enters information or asks questions related to a specific problem. For example, in a medical expert system, the user may enter symptoms such as fever, cough, or headache. The user interface is the communication layer between the user and the system. It collects the user's information, sends it to the inference engine for processing, and finally displays the system's recommendation or diagnosis. A good user interface should be simple, interactive, and easy to use so that even non-technical users can operate the system without difficulty. In modern expert systems, the user interface may also explain how the decision was reached, increasing transparency and user confidence. The knowledge base is one of the most important components of an expert system because it stores all the knowledge required to solve problems. It contains two main elements, facts and rules. Facts are pieces of verified information about the problem domain. For example, a patient's body temperature, blood pressure can be considered facts. Rules describe how the system should reason using those facts. These are usually written as if-then statements. For example, if the rule says if a patient has fever and cough, then the patient may have influenza. The expert system can use this rule to make the diagnosis. The knowledge stored in the knowledge base comes from experienced professionals such as doctors, engineers, financial experts, or scientists. Without a well-designed knowledge base, the expert system cannot make intelligent decisions. The inference engine is often called the brain of the expert system because it performs the reasoning process. Its job is to compare the user's input with the rules stored in the knowledge base and determines the most appropriate conclusion. The first step is rule matching, where the system identifies all the rules that match the current facts. Sometimes more than one rule may apply. In such cases, the system performs conflict resolution to decide which rule must be executed first. After selecting the best rule, the inference engine applies logical reasoning and produces the final recommendation or solution. This reasoning process enables the expert system to solve problems in a systematic and intelligent manner, similar to how a human expert analyzes a situation before making a decision. This slide introduces three important supporting components of an expert system. First, working memory is a temporary storage area used during problem solving. It stores the user's current inputs, intermediate results, and information required only for the current session. Once the problem is solved, this information is cleared. Next is the domain expert. A domain expert is a specialist who has deep knowledge and practical experience in a specific field. For example, a doctor is the domain expert for a medical expert system, while a financial analyst is the domain expert for a banking expert system. Finally, we have the knowledge engineer. The knowledge engineer works closely with the domain expert to collect, organize, and convert expert knowledge into logical rules that the system can understand. In simple terms, the domain expert provides the knowledge engineer structures that knowledge, and the expert system uses it to solve problems accurately. This slide explains the two main reasoning techniques used by expert systems: forward chaining and backward chaining. Let's begin with forward chaining. Forward chaining is known as a data-driven reasoning approach. It starts with the facts that are already known. The inference engine continuously applies rules to these facts until it reaches a conclusion. For example, if a patient has a fever and a cough, the system starts with these systems and applies rules to conclude that the patient may have influenza. Now let's look at backward chaining. Backward chaining is a goal-driven reasoning approach. Instead of starting with facts, start with a possible conclusion or a goal. The system then works backwards to check whether enough evidence exists to support that conclusion. For example, if the goal is to determine whether a patient has influenza, the system checks if the patient has symptoms such as fever and cough. In summary, forward chaining begins with facts and moves towards a conclusion, while backward chaining begins with the goal and searches for supporting facts. This diagram shows the complete working process of an expert system from start to finish. First, the user enters a problem or a query through the user interface. The user's input is temporarily stored in the working memory. Next, the Inference Engine analyzes the information and searches the knowledge base for rules that matches the user's input. Once suitable rules are found, the Inference Engine applies logical reasoning to evaluate the facts and reach a conclusion. Finally, the expert system presents the result or recommendation back to the user through the user interface. This structured workflow enables the expert system to solve complex problems efficiently while maintaining consistency and accuracy. This step-by-step reasoning process is what makes expert systems valuable in many real-world applications. Let's understand how an expert system works using a medical diagnosis example. Imagine a person visits a hospital. A patient visits a hospital and reports symptoms such as fever, cough, and body pain. This inference engine compares these symptoms with the if-then rules stored in the knowledge base. For example, one rule may be if a patient has fever and cough, then the patient may have influenza. The inference engine evaluates this rule along with other available rules before producing the most appropriate diagnosis. Finally, the system displays the diagnosis and may also recommend suitable treatment or suggest additional medical tests. This example demonstrates how expert systems assist doctors by providing quick, consistent, and evidence-based recommendations. However, the final medical decision is always made by the healthcare professional. Like every technology, expert systems have both advantages and limitations. Let us first look at the advantages. Expert systems provide fast and consistent decision making, reducing the chance of human error. They can work 24 hours a day without getting tired, making them suitable for continuous operations. They also preserve expert knowledge, ensuring that valuable expertise remains available even if the original expert is no longer present. Now looking at the limitations, traditional expert systems cannot learn automatically from new experiences like machine learning models. They also lack common sense, creativity, and human intuition. In addition, building and maintaining an expert system requires significant time, cost, and continuous updates by knowledge engineers. Therefore, expert systems are most effective in well-defined domains where the rules are clear and structured. To conclude, expert systems remain one of the most important applications of artificial intelligence. Although they were developed several decades ago, they continue to evolve by integrating with modern technologies. Today, expert systems are being combined with machine learning, enabling them to improve their performance using data while still applying expert knowledge. They are also They're also being integrated with generative AI and large language models, making interactions more natural and improving the ability to assist users. In addition, cloud computing allows expert systems to be accessed from anywhere, making them more scalable and widely available. These advancements are expanding the use of expert systems in healthcare, finance, education, cybersecurity, and many other industries. In conclusion, expert systems continue to play a vital role in intelligent decision support and will remain an important part of the future of artificial intelligence.